Perfect. So welcome everyone. This is our 31st event. Summers is almost gone. We have the rain here and autumn is finally coming in. So here is our autumn event. And with that, we have our September meetup for today. But before we move into the session with two amazing speakers, I would like to talk about why PyBerlin and why do we have this platform in the first place. But before I forget, I am Shreya Agrawal. I will be your host for the first half of this evening. And let me quickly talk to you about why PyBerlin. So we all love Python and we love sharing ideas. So when the Python came to Berlin, it climbed the TV tower and said, "Hey, Berlin, hey, I'm here." And that's why we have this platform of PyBerlin. We're all based in Berlin and we welcome everyone who is interested. The organizers are Anastasia, who is managing the streaming platform today. I, Shreya Agrawal, and we have Theo Kostia and Lyubin Alexandrov, who you will be interacting with throughout the session. We all work behind the scene to make these events possible for you, and we hope you like it. And if you have any feedback for us, then please let us know how we can improve it. Or if you like something about it, then do let us know that we did a good job. We would be really happy to hear that from you. We do not have many rules and regulations, but one thing that is super important for all of us, be the organizers, speakers, or the audience, is that be nice to everyone, be patient, and everyone is working hard to make this a successful event. Some glitches can be there here and there, but be patient, be nice, and we will all have a good time. For more rules and regulations about our platform PyBerlin, you can read our code of conduct on the link mentioned on the screen. It is a very safe place to ask questions. There is no need to feign surprises or well actuallys or any just or subtle isms. By subtle isms, we refer to racism, sexism, or any form of discrimination. And whatever questions you may have, please feel free to ask us. You will be told how to ask questions. You can just post them on the Zoom link, or there are other means as well that will be talked about later in the session. Today's event is sponsored by ScoutBee, and Anastasia made it possible. So thank you to ScoutBee and Anastasia for making this, for helping us with the Zoom links and making this event more smoother by using Zoom, by using a professional Zoom account. Today's agenda, we have two very interesting speakers for today. First speaker for the evening is Ondrej. He will be talking about automated machine learning with Keras. Ondrej is a data scientist at Trayport, where his team tries to use artificial intelligence to make energy and commodities trading better. Sorry, before that, he was an astronomer. And if you're interested in galaxy clusters and celestial bodies, he is your go-to person. Super excited to have you, Ondrej, and we will shortly be listening to your experiences with automated machine learning. And the next speaker is Ellie Holderness. Pointers in my Python, it's more likely than you can think. Very interesting topic. And Ellie is a developer's advocate at Anvil. And in her free time, likes to grow plants, knit, and play video games. Looking forward to hearing what you have to say about pointers as well and your experiences with Python, Ellie. Before we hear our speakers, we would just like to tell you that we're also looking for organizers. If you would like to be somebody who makes these events possible, to contact speakers, organize these slides, or just know how these platforms work from behind the screen, then let us know, and we would be very happy to have you on our platform. And at the same time, we're always looking for speakers. And by speakers, do I mean professional speakers only? Well, not really. We are looking for people that have something to share. Any idea, or if you're preparing for a bigger conference and you would like to share it with our audience, then we would be happy to have you with us. We have two formats of talks. One is the 30-minute talks with Q&A, but actually you can decide if you want to have Q&A or not. And then we have shorter 5 to 10 minutes talk, lightning talks. This is more for a quick introduction about something, or if you did a personal project and you want to share your learnings with our audience, this is a perfect format for that. And if you're interested, then please submit your proposal here on using the QR code mentioned on the screen. Alternatively, you can contact us on Twitter or reach out to one of the organizers and just let us know that you have something to talk about on our platform, and we will for sure make it possible to decide something that is mutually convenient. And also, we are active on Twitter. So if you have something interesting to share, good or bad, or some feedback, then please do so. And when you do that, please don't forget to tag us. Our handle is PyBerlin Python. And also for this amazing slides that you saw just there and the logos that you saw, these were created, the free assets and resources were created using Slides Carnival, and the photographs were by Unsplash. And the people who helped with this logo and story creation is Elena, Konstantin, and Christian Barra. So thanks to you all. We have been using your contributions to PyBerlin for the last 2 years, or more than 2 years, I think. And we highly appreciate these logos and stories and the slides that you have helped us create. And with that, I would like to transfer the platform, the stage to Ondrej, and he will be talking about automated machine learning with Keras. So Ondrej, over to you, and looking forward to what you have to share.
Thank you. Let's see whether I can manage all these buttons and this button. And now I should be sharing the screen. Thank you. So yeah, thank you for your very nice introduction. Indeed, I will be talking about automated machine learning with Keras. Also, sorry about not keeping eye contact. I have it here, so I will be checking there. So first, quickly about me, even though it's already been said, the picture of me proving that I don't have headphones all the time, it's only the latest fashion. Originally, I come from Slovakia. I studied astronomy, so if anything, we can also talk about, let's say, galaxy clusters. Then I worked as a data scientist, dealing with, let's say, infrastructure applications in Netherlands and partially in the UK. So if you want to know about the traffic or water management, I know a little bit. And since about the beginning of this year, I've been a data scientist at Trayport here in Vienna. Trayport, just for a quick shout out, is a company that creates and maintains software for trading of all kinds of energy related things, being directly electricity or different kind of commodities that can turn into energy and electricity. If you are using electricity at any point, like now, there is a decent chance that software from Trayport was involved at some point. And as a quick shout out, we are hiring, please, and go visit our careers page. Last time I checked earlier today, there were around 25 open positions, mostly technical, mostly in London, many in Vienna, some in Singapore, so you have a choice. Trayport is a nice place to work. We are a finalist in this employee benefits competition, so the company really takes care of you, and obviously you see all the smiling people in the pictures. And with this said, we can get to the automated machine learning itself. So probably as many technical people, I also like to, at least from time to time, consider myself a bit of a cynic. And as a cynic, when I think about progress, I mostly think of it as coming in 2 steps. And these steps are laziness and chasing away disappointment. So human beings are lazy by nature. They always have things that they want to do. And they would like to outsource it. And lo and behold, every so often there comes a genius or a team of geniuses that say, here, I've invented this thing, and you can indulge in your laziness. This thing will do this for you. That's the laziness step. People are happy. People think that the problem is solved. But as soon as they start using it, they will realize that, well, they've been overpromised, and a lot more progress needs to happen before this magical thing turns into what they hope it would be. Now, with an arrogance of a physicist that I used to be, we can try shoehorning this story on computers that I know nothing about. And how would this go? Well, the laziness part comes from thinking itself. Thinking is hard, you can be wrong, it's unpleasant. And so since a long time ago, probably from Gottfried Leibniz and even easier, people have been wishing that there was something, a thinking machine, that would take this pain away and people would never have to think again. And at the beginning, or at the first half of the 20th century, someone actually invented a computer, or a few someones, and everyone rejoiced until they, like we said, started using it. And suddenly people realized that, okay, you can argue whether these machines think or not, and probably they do, but it's just so complicated. They think in these all kinds of non-intuitive ways that you need an expert to really efficiently communicate to these machines what they should be thinking about and how they should be thinking about it. And not even at the beginning, but after decades of development, you still need the developers. They are in high demand, they are well paid. Even though we now have tools like object-oriented programming that makes it slightly, that makes thinking of us and of the computer slightly more compatible, you still need a lot of these people, these experts, to deal with this. We can do another shoehorn from a similar thing with machine learning. The laziness comes as a laziness to model. You have nature, you want to describe it, you want to predict it, and it's tough. And here comes machine learning as this magical tool that can automatize this for you. You will take some data, ideally gathered by someone or something else. You give it to the machine, you tell the machine what you want the result to be, and the machine will somehow deal with this. So it's completely magical. You don't have to deal with this. You can start your Margaritas Tuesday earlier. However, many of us probably know it's not as easy. You, as a data scientist, spend a lot of time manually dealing with a lot of things. You need to be an expert. It's tough, etc. Even though since the beginning, where you really had to type up your algorithms, we've come a long way. Now we have these dedicated libraries like scikit-learn, or platforms such as we will be talking about, Keras. You still need an expert, even though the beginnings of what we call the automated machine learning are starting to appear. So let's see what this automated machine learning might be. In this talk specifically, we will be talking about the automated hyperparameter searches, automated machine learning. And to be on the same side, let's really start from the very beginning. So here you see a schematic of a neural network, a multi-layer perceptron that you've probably seen many times. The data or the numbers move from left to the right. You probably know that in this schematic, each of the arrows means a parameter, and there is 64 of them. Now, when you are training the model, which means showing the model the data and telling it what the result should be, the parameters themselves, of which we have 64, in this particular case, get assigned automatically. So this is great. However, the model has hyperparameters. The hyperparameters are things that we, as the data scientist or the person that is coming up with the model, needs to set themselves. Usually needs to set themselves, and they define, let's say, the architecture of the model. Typically, there is many more parameters than hyperparameters, but you need to find good hyperparameters because they kind of, the performance of your model depends on it. So for our particular case, we could say we have, let's say, 3 hyperparameters, which would be the sizes of this internal, as we call, hidden layers. So unfortunately, the answer to the question how to find the best hyperparameters is not really that easy. There are algorithms how to do this, but there is no, let's say, golden or the silver bullet, as they say. So here we are listing a few algorithms that you can in general use for his hyperparameter search. The first is obviously the grid search that you could come up with in a few seconds of thinking. For each of your hyperparameters, you take a set of values that you want to try, and then you use a combination of these for, well, all your hyperparameters. This is illustrated here in the bottom left, if you actually see my cursor, where the colorful, the colors in the background are this hyperparameter space and show the performance of the model. And we see that we have some grid of points where we take those hyperparameters, we train the model, and we look at the performance. And ideally, we would take the model, the set of hyperparameters where our model performs the best. Let's say it might be the blue one here at number 9. Now, this grid search has the disadvantage that it gets very computationally expensive very quickly, and also that you might actually miss some interesting spots. So for example, if this blue between 1, 2, 4, and 5 was really the best place, well, we will just never find it. Another algorithm is the random search, where you don't really set the values that you want to try, but more like distribution from which you draw the values of your hyperparameters. So this might look more like this thing on this figure on the bottom right, where, yeah, you just randomly shoot and hope for the best. Here you can get both lucky and unlucky. You can hit on a very good performance. You can completely miss it because, well, it's random. To tackle this, at least partially, there is the algorithm called the Bayesian optimization, which tries to remove the randomness by making the assumption of how this underlying hyperparameter space looks like, so this colorful space underneath. And then, instead of drawing completely random sets of hyperparameters, it tries to guess where it should go next, either somewhere where it hasn't explored before, or even better, where it suspects that it will get good results. So this is great. Similarly, you can use this Hyperband algorithm. How this works is you start training of your model in a parallel fashion with a lot of different sets of hyperparameters. And as you go, this algorithm very quickly tries to predict whether a particular set of hyperparameters is likely to turn into a good model performance. With many of these, it decides that this is not a promising venue. It takes away the computational resources from this training and assigns it to one that it considers promising. And so you kind of zero in to what the algorithm considers the best. So these are some examples of the algorithms, and now how we can actually use it, or what tools allow us to use it if we, let's say, don't want to write them. So as the title of this talk indicates, we will be talking about the Keras library, which is the very widespread library, or maybe even a platform allowing us to build deep learning models, so the neural nets. And within the context of the Keras ecosystem, there exists two tools or two libraries called Keras Tuner and AutoKeras that implement these algorithms that we've just talked about to make our hyperparameter search easier. So Keras Tuner itself is a part of the Keras library. So if you've installed Keras, you already have it. AutoKeras is a wrapper around Keras Tuner. It's been developed in collaboration with Keras, and both of them are really nice. So in the rest of the talk, we will be going through some examples of how these can be used. And specifically, we will take a toy problem and look at how 3 different people with different levels of machine learning knowledge, of progressively decreasing knowledge of machine learning, how they would use this to solve this problem. Now, this indirectly brings us to the start of the talk, where we said that, well, for machine learning and artificial intelligence, we still need experts, but maybe these and automated machine learning in general are slowly starting to get us the steps to get this machine learning for the masses, to sound very revolutionary about that. So something that make these tools more widespread. So the problem that we will be dealing with is one that many of us probably interacted with in many forms already. It's this MNIST digit classification. So we will have a lot of images of handwritten digits that look like this grid that we have. And we will want our models in the end to be able to tell which digit is shown in which of these images. Everything I will be talking about is also in this notebook available on Git. I will be actually sending the link in the chat, or maybe Anastasia can help me and send it to everyone. And in any case, you can download it and play with the tools yourself and have a go. And so with this out of the way, we can actually start with our first example. And the first person trying to solve this toy problem will be someone that we will call a data scientist. A data scientist has machine learning domain knowledge. Depending on how arrogant they are, they might even say good machine learning domain knowledge. And what they would like to do within the context of this problem is also retain a lot of control of what's going on, both because if certain issues, errors, bugs, etc., were to come up, they would like to quickly zero in on where these problems are and solve them, and maybe also to gain some insights. Maybe the algorithm that they will be using does something unexpected that might allow the data scientist to learn a new trick. So what will the data scientist do? Let's say that somewhere in their code, they have a function that looks like this. Function called build model that has a lot of Keras-like code in it that prepares our neural net. So it prepares the layers, as we saw before, neural nets come in layers, prepares, compels the model, and in the end returns it. So let's say how these individual steps might look like, again, by some code snippets. The layer definition might look like this. Now, if you've ever worked with the Keras functional API, this is where it comes from. This is how you define the individual layers. For example, in this first example, you define the convolutional layer, which is an instance of this conv to the object. Then you have some in red and blue parameters, or to call them correctly, the hyperparameters. So these are the ones that we will be dealing with, the best looking for the best values of them. And this instance of this conv to the object that then gets connected to, let's say in this case, the input layer, so the preceding one. Similarly here with the dropout layer that has a different set of hyperparameters, in this case just the rate, which is connected to some kind of a previous layer. And finally, we might have some output layer, which is a dense kind of a layer that connects, for example, to the previous dropout. So this is how you define the layers. Then you need to do what I call the prepared model, which is pretty much connecting your model to the outside world. So you tell the model where the data comes in from, in this case, the input layer, and where are the outputs then channeled, where you can get them from. So this would be the output layer. This is it, nothing much very exciting. And finally, you need to compile the model, so prepare it for the training, add some more bells and whistles. Most importantly, defining the optimizer, which will drive the training, so which will drive the most efficient way to get the parameters to their best values as soon as possible. And here you can again have a hyperparameter like a learning rate. So this is how it looks like, and you, because of how we set it up, this is actually quite clunky. Why is filters 32? It might be bigger, it might be smaller, etc. Whatever we want to change in this model, we want to go into the function and manually change. And we would need to do this again and again to find the best possible performance of this problem. So let's try updating this function a little bit to be compatible with these automated machine learning frameworks that we are discussing. So here are 3 code snippets from the previous slide that we will be updating. And one by one, first we update the function itself. Before it had no inputs, but right now we give it on the input this HP object, HP standing for hyperparameters, but it is just an input. And then we can use it inside. So we will, for example, make this definition of the convolution layer much more verbose. While before we had hard-coded values for these hyperparameters, filters, and kernel size, now we, instead of defining the values, we define some kind of distribution or some kind of a set from which we are getting the values. So filters, we want to be an integer with the minimal value of 16, let's say maximal of 128, and we want this to grow in steps of 16. Similarly, the kernel size, which previously we set to 3, now we tell the function to choose one value from 1, 3, and 5. Now you could argue that you could turn one example into the other, but here we have both things. Similar, this syntax that we've just introduced is not just limited to the layers that you have, but any kind of parameter that you set inside of your function. So for example, this optimizer that we have, we can also change from a set value to, let's say, a choice of several different ones. So with these examples of how we might update the code, we can now move to the actual automated hyperparameter search. We will be using this Keras Tuner part of Keras. And first we import, let's say, Bayesian optimization. So this is one of the algorithms that we discussed, but there are all the others. Then we take our function that we've just updated. Now it has the HP input. And we take this function and plug it into this definition. So we define something that we will call tuner, which is an instance of this Bayesian optimization. We define that the hypermodel, so this is some kind of an object that generates our models according to some rules. Here we plug our function that defines the models. We can also do this with a class, and the example in the notebook is with a class. We also need to give it the objective, which in this case will be validation accuracy. This tells the tuner, if it sees 2 models, which one is the better one, which one it should consider the better one. And we are ready. So first we load the data like this in the top. As we said, this MNIST digit classification is a very well-known data set, very well-known problem. So there is a function we can directly load the data. We need to do a bit of normalization of the data, so a bit of processing manually. But with that, we can just run tuner.search, give it the training data and targets, the validation data so that it can check its criteria, and set it to run. Actually, let's just have a quick, let's say, look at the notebook that you can get from GitHub and play with yourselves to see how it will work. So the notebook is quite verbose, so you can read this yourselves, but ultimately we do our imports, which of course now take forever. We load and normalize the data in this cell. Again, the details are not that important what happens, but we see that here we can show that for an image that says 0, it says it's a 0. And here is the class that generates the models in the slides we had a function, here we have a class, but it's the same. The class itself has a method called build, and this method itself takes the HP object that we saw before as the input, does several things, and returns the model. So this generates the model as we want it. It has the code that we saw in the slide. So for example, here it has this choice of a learning rate of out of the 3 that we had. So let's define this. Here we define our tuner. It has a few more options or a few more parameters set, but they are all commented. We can check how we define the parameters. And then we can start running this tuner.search. And once I start running it, it will start giving an output on how it's training. So it contains a lot of information. Let's go back to the slides and actually look at what we see there, if it ever loads, which it should now. So the output looks something like this. You go through one trial at a time, let's say in this case, whoops, in here. And for this particular screenshot that I did from the notebook that we just saw, we see that it finished the 3rd trial when I took the screenshot with an accuracy of almost 90%. It also tells us that best validation accuracy so far was over 94%. It's been running for 1.5 minutes when I took the picture. And currently it's running trial number 4 with this set of hyperparameters. It compares it with the ones that it got the best performance so far. And here at the bottom, it shows the progress of the training for the current epoch. So again, if you used Keras, you are familiar with this thing. So it gives you quite a lot of information. You can, for example, as a data scientist, look at how the current values are different from the best ones so far, and maybe start telling the stories to yourself like, okay, maybe I want a deeper neural net rather than broader or something like that for my particular problem. But this is essentially what you would do and how this Keras tuner can help you with your automated hyperparameter search. So this is what the data scientist will do. Let's now quickly go through what the second person, how the second person on our list would solve this problem, which I call the technical manager. Now, this is someone that knows a bit of programming and also knows a little bit at a very high level about how machine learning works. They know a few concepts. And the interesting thing is that these tools we are talking about allow this technical manager to translate these concepts directly into the code. So let's see how this would work. And this is, again, all in the notebook. So let's start with the code immediately. We will be using AutoKeras, so this wraparound Keras tuner here that we import. And now we start building this kind of auto model or hyper model or whatever we call it. Well, for this, we will essentially use a similar syntax as with the Keras functional API. So defining something like layers, which are called blocks now, and connecting them to one another. So the technical manager knows the first thing is that this is a problem that has images on the input. So they define the input node as the image input. Then they know that for the neural nets, you need to pre-process the data. You need to perform the normalization. And whatever it is, the auto model will probably take care of it. They just need to explicitly add it. So they add normalization and attach it to our input node. Then they know that it's a computer vision problem, and hence they should use convolutional neural nets because they tend to perform well on computer vision problems. So they attach this convolutional block there. And finally, it's a classification problem. So we finish this, or this technical manager wraps it up with this classification head. And this is pretty much it. All these empty brackets here can contain specific parameters, but they also have decent defaults, so we can just define it like this. Now we put it all together, similar to before. We say where the data comes in, where it comes out, and what is the objective. And then we have our auto model ready. We can load our data just as we did before. Now we don't need to perform any normalization. The model will figure it out by itself. And we run automodel.fit. This is similar to the Keras Tuner.search that we had before, but the functionality is before. This fit calls the search underneath. And once you start running it, you get a very similar output as we had before, where it is now, what was the best so far, what is it doing in detail now, and how does it compare with the best one. The parameters are now slightly more. And in the end, what is its progress. So this is how the technical manager might want to deal with this. And finally, moving to the third person, which I very hesitantly, because of at least my own job security, call the data scientist of the future. But if you want, you can also replace it with your parents or your grandparents. The point is that this person doesn't really know anything about machine learning, and this person basically allows us to maybe go towards what machine learning has been advertised at least as the start of this talk as. So this thing where you take the data, the targets, and let the computer figure out everything. So let's see what they will do. Again, they will use AutoKeras, as we talked before, but now the only thing that they do is the problem setting. They know that they want to use machine learning, so they define an auto model. They know that they have images on the input, so that's what they will tell it. They also know that it's a classification problem, so there will be a classification output. And that's pretty much all of it. They load the data, as we saw before, and automodel.fit, they can run this. Even better, since this is a very widespread problem, this has been prepackaged into this object called image classifier that can be used, but the rest of the code is the same. So from the import to the fitting is really just a few lines of code. And again, once you start with this, the usual output, where is it now, what it's been doing in detail, and the progress bar. So this is maybe the first steps to the data science of the future. And this is pretty much it. So in this talk, we've been talking about automated machine learning, specifically in about the automated hyperparameter search. We looked at how it might make our lives as data scientists easier, but also how it might allow access for the non-experts into the field and maybe make them more curious to learn. And specifically, we talked about the Keras Tuner and AutoKeras as nice tools for Keras that are definitely worth exploring. And with that, I'll thank you for your attention.
Yes, thanks for the talk, Ondrej. So now we have time for some questions. So if someone on the call or on the Twitch stream has a question, type it in the chat and I will relay the question. I can start maybe with one question. I think it was on slide 18, if I'm not mistaken. I was wondering which algorithm is used for the search. So they're like grid search, random search.
So by default, like I said, for this particular one on slide 18, we defined it here. So we said it will be the Bayesian optimization. You can also there is a hyperband object, etc. So the way you define the tuner is the way you define the algorithm used.
Ah, okay, I see. Yeah, thanks. All right. Are there any other questions? So there we have a question: for which cases would you use which? So assume for which cases would you use which algorithm for finding parameters?
As obviously the disappointing answer is it depends. Specifically, let me think a little bit. I guess it's probably thinking about it. Maybe I would start with at the early part of the problem solving with the hyperband, because it might be quicker. It's this massive parallel, like we said, this massive parallel thing that quickly zeroes in on let's say a good solution. So maybe this can get you going quicker, but maybe later I might switch to Bayesian optimization, which can maybe get to a better result. But ultimately, I guess if you just focus on one, you might not really get any much worse results. So it might not matter that much really, and you can just try more of them.
Thanks. I have a follow-up question. So in your experience, when you use different algorithms for finding the perfect optimal hyperparameters, does it make big difference if you use one or another algorithm? Like experience, yeah.
Yeah, so I mean, I must say, in my experience, in my very limited experience, because it's, I mean, this tool is something that I also discovered relatively recently. So there's been only limited, let's say, opportunity to play. Though, I mean, it's tough to answer because of, let's say, personal biases. I would hopefully be able to count myself among the data scientists, in which case you don't really want to push or give that much let's say of the control away. So ultimately you might still go in and do a bit of manual search. So I actually am not able to answer. I don't know which one is really better. You play with one, you play in the other. Maybe you pick your favorite, and there are also then others. So yeah, it's sorry, it's really a non-answer.
Got it. So we have actually another question from Gerald. When would you use AutoTuner and AutoKeras?
Yes, so I think they are kind of complementary. The AutoKeras I would use potentially for slightly more pedagogical purposes, where you want to quickly show someone or allow someone to get to a relatively good result without that much work. But then what I would do is get this person to actually explore the AutoKeras code, which contains a lot of default values for different variables, and different ways things are put together. And ultimately, AutoKeras, like we said, is the wrapper around Keras Tuner. So internally, AutoKeras call Keras Tuner and can then give you like a very good use case how to learn to use Keras Tuner well. So ultimately, I guess the tool would be Keras Tuner, because it gives you much more control, which probably as a data scientist you want to have.
Got it. Thanks. If we
I
don't
have a question.
more questions, maybe we can move to the break.
There's somebody who wants to ask the question.
Yeah,
I have one question. So hi. Yeah, my question is, so I've worked with other AutoML libraries before, and in my use case, I want to solve a problem, but also inference time was important. And the issue that I had is that in most cases, the AutoML algorithm would find a good solution, but then it would create a very complex model, and then the inference time was too long. Do you know if in AutoKeras it's possible to also optimize for that, for inference time?
So I am not aware of it being directly, explicitly being able to consider the inference time. However, I guess you can do this very indirectly by limiting the parameter space or something. So you would shrink your model artificially or something like that. But I don't think you can really do this inference time limitation.
Okay, thank you.
All right, thanks. So if there are no more questions, then thank you again for the talk, Ondrej. And
thank you for your attention.
We can start with the second talk, Pointers in My Python. It's more likely than you think, by Eli Holderness. So Eli, feel free to start with your talk.
All right, can you see my screen?
Yes.
Fantastic. All right, let's get going. My name is Eli Holderness. I'm a developer advocate at Anvil, and I'm here to talk about pointers in Python. This is a whistle-stop tour of some of the ways that Python handles objects in memory, with a particular focus on CPython's implementation of that memory management. So we're a little bit, I have to race a little bit to get this within half an hour, so pardon me if I go quite quickly. In today's talk, we are going to be learning about what pointers are and where you'll find them in your code, what the ID of a Python object is and why it's relevant, and how CPython can tell when you're done using an object that it has in memory and what it does at that point. So to start with, what is a pointer? Well, a pointer is something that points at an object. But what does that mean? Here are some examples of pointers. Here's me. I've got a name. My name is Eli. But I have more than one name, or more than one way that I am known, more than one thing that points at me. So for example, I have a Twitter handle, @Eli Holderness. I also have a Hebrew name. And there are many other ways that you might be able to refer to me. So that Anvil developer advocate with blue hair. These are all pointers to the same object, me. And pointers in your Python code work in quite a similar way. So let's see some examples. So pointers are objects in the namespace that correspond to objects in memory. When you have a variable, it corresponds to something in Python's memory. That's the actual object that has all its attributes and all of its sort of methods that you might call on it. So for example, you have an object called myClassInstance, and that is a pointer to the actual memory object. So in the examples that we're going to be using in today's talk, I'm going to be using a lot of lists, and that's because lists actually contain pointers in quite a useful way for illustrating the ways that Python handles memory. So if I've got at the top, you can see a bit of Python. A is set to equal a string and immutable object inside a list. What's actually happening there is A points at this list object in memory, and that list object contains all of the machinery that comes along with a list. So being able to append to it, being able to get items from it by the index, and also all of the contents of that list. And those are stored as pointers to the contents, not the actual contents themselves. So you can see in this little diagram here, kind of how it works. And because of the way that lists handle memory, we're going to be using them for a lot for the examples that we do in the next few sections. So one of the behaviors that you might see in Python, and something that often trips up newcomers to Python, is something called pointer aliasing. And this is the behavior that you sometimes see where you change a variable without meaning to. You change one thing and another thing changes, even though you never actually thought that you changed it. And we're going to be seeing exactly how that can happen. So the example we're going to be starting with is this list. A is a list containing the strings my cool list. We've defined it, we're getting the interpreter to print it back out to us. Now, if I set B is equal to A, let's say I want to make a copy of A. I'm going to set B is equal to A, and I want B to be my awesome list instead of my cool list. So I'm just going to change the value of the second string within B, the B1. I'm going to set that to be awesome. Great, cool. We print out B and it says my awesome list. But then if we look at A again, we see that A has also changed, but we changed B, not A, right? Well, not quite. B is just another pointer to the same list object that A represents. So when we changed B, we were reaching the same object that A references. The way we can get around this is to use the copy method on a list. So if we set C is equal to a copy, and we want to change C to be my amazing list, we can do that. We can get the interpreter to print it back out for us. So we see that the change has been made. And when we look at A again, we see that A hasn't been changed. And so what's happened here is that when we do a copy, it actually creates an entirely new list object. And so when we change C, we don't change A. However, what if we have pointers inside our pointers? What if we have a list within a list? So here we're doing just that. We've got our list A, and we're going to set it to a list with one element, and that element is itself a list with Alex and Beth inside it. So again, we've defined it, we're getting the interpreter to print it out. So what happens if we do the second thing that we did before, copy? We're going to make a new list object. And now we want to append Charlie to the list inside our outer list. Well, we can certainly do that. We can mutate the list inside B, and we can get the interpreter to print it out for us, and we can see that that's happened. However, when we look again at A, we can see that that one has changed too. And the reason for this is that when we do a copy, it makes a new list object, but those pointers inside the list object still point at the same things underneath. So because we had a list within a list, when we made a copy, it still pointed to that same list. So what if you don't want that behavior? What if it's pointers all the way down? You've got a list that contains a list that contains a list, or other mutable objects, but you do want to make an entirely new copy and avoid this pointer aliasing entirely. Well, there's a module called copy within Python, and it has a method called deep copy. And you can just use that to make an entirely new copy of your entire object. So going back to our example with a list within a list, we've got our list A, we're going to deep copy it. And now we're going to append Dan to the list within a list, Alex, Beth, Charlie, and Dan. And if we go and look at our original one, our original list, we can see that it hasn't been changed. And this is because deep copy actually makes entirely new infrastructure of all the objects in memory. None of the references are the same. Nothing is pointing to the original objects. So I've got some diagrams to illustrate exactly what's going on here, because it is quite abstract. Equals makes a new pointer to the same object. So we've got our list A that points at an original object in memory, and other things that are pointed to by that object. When you set B is equal to A, all you're doing is making a new pointer to that original object. And this is why you have the thing pointer aliasing, where if you change B, you change A, because they're pointing at the same thing under the covers. If you do copy, what happens is it makes a new object in memory. But because lists contain pointers, you still have this issue where if your things that the list points to are changed, that is reflected in both of the objects. You can see that they're both these white boxes are pointing at the orange box underneath, the same one. And this is why copy isn't enough. But you can see that it's doing something different to just setting B equal to A. Sometimes it'll be sufficient, but in the case of lists contained in list, it's not enough. And that is when we have deep copy, which makes an entirely new object and copies the values all the way down. If we had more than 2 layers here, it would still copy all of them all the way down. And I've added this blue bar in the middle there, so you can see that they're completely disjoint. So you've got your A, your original object in memory, and everything it points to. And if you do a deep copy of that, it makes not only a new object in memory, but new things for that object to point to. So even if you modify B to your heart's content, it will never be reflected in A. So this is some illustrations of the way that Python handles objects in memory and the ways that copying works. And we've been using lists, which are mutable objects. What happens if we look at some immutable objects? So here I'm going to show you an example of some perhaps unexpected behavior in Python. So a tuple A is immutable. It's essentially an immutable list. Once you create a tuple, all the values that are its elements are frozen in place. You cannot change them, which means that if you have a pointer, that pointer's value must always be the same. It must always point at the same object during the lifetime of the tuple that it's contained in. But what if the thing that it points to is mutable? So for example, what if we had a list within a tuple, which is exactly what we're doing here. We're setting a tuple. You can see it's got orange round brackets around the edge to demonstrate that it is different than a list. It is a tuple and it is immutable. And the first object of our tuple, the first element, is a list. And we can append to it if we like, because we can do that with lists. And we're going to do that. We're going to add 4 to our list of numbers. And that's all fine and good. We can mutate a list in place, even if it is what is pointed to by the first element of a tuple. However, what if we wanted to use a different method to do exactly the same thing? There is something, the plus equals operator. So what if we wanted to add 5 to our list and we use the plus equals modifier to do it? Well, it gives us an error, as you can see. And this is because you cannot assign to the elements of a tuple, which is exactly the error that it's giving us. Tuple object does not support item assignment. So far, so good. This is what we expect. But if I now go and get the interpreter to print us out that first element of our tuple A, you can see that 5 is actually there. So when we did that operation, the plus equals, it gave us an error to say, no, you can't do that, but it did it anyway. And this is because when you use that plus equals operator, first it mutates the list in place and then tries to assign it back to itself. And the first part goes off without a hitch. We can mutate objects with the elements within a tuple, but we can't assign to them. So it gives us an error after it's already done the thing that we wanted it to do, which is, you may not expect this, and it's quite a common Python gotcha. So if you ever have interview questions that ask you for unintended memory management behaviors, this is one to remember. Right, so we've looked at what happens when you try and copy objects, the various ways that you can do that, by assignment, by using the copy method, or by using the deep copy method. But what that is all sort of referring to under the hood is whether 2 objects are actually the same thing. And the way that you can tell this canonically is by object IDs. So you can get the object ID of any object in memory while you're using Python by calling the ID function on it. This is a built-in function that you can call on any object, and it will always return you, regardless of the implementation of Python we're talking about. We're not yet talking specifically about CPython. It will always return you a number that is unique, an integer to be precise, that is unique and constant for the lifetime of X. As long as this object X exists in memory, you know that the number that ID gives you when called on it will be unique and constant. So most Python implementations, or many I should say, use the object's address in memory as its ID. And this is what CPython does, and it's what we'll be seeing as examples throughout the rest of this talk. But it's not true of all Python implementations. So for example, CPython uses the memory address, but Sculpt, which is a Python to JavaScript compiler, actually, whenever the ID function is called, it generates and caches a random number that is then assigned to that object and stays with that object for its lifetime. So you cannot necessarily rely on the idea that the ID of an object corresponds to its memory address. However, just to go back to that, the memory address is a really good choice as to for something to use, because it will have to be unique and constant for the lifetime of an object, because that's where that object lives. Another object can't live there, and it will have to be constant, because if the object moves, then it won't be the same object. So let's see some examples. I'm going to go back and define a list again, and I'm going to call the ID on it, and you can see it prints us out this long number. If you are familiar with programming in C, you might recognize this a bit more easily if it was in hexadecimal, but because it is the value of a pointer, it is in fact the value of the pointer A to that list object in memory. But as far as generic Python is concerned, it's just a number. So if we set B is equal to A, and this is the way of making a copy, which is really just making another pointer to the same object in memory. If we call the ID function on both of these variables, you can see that they have the same ID. They're really referring to the same object in memory. If we do C is a copy, however, you can see that they actually have 2 different IDs. They're referring to 2 different list objects in memory. And so this leads us to a question. When are 2 objects actually the same? Because obviously if you do a copy, C and A are kind of equal in some ways, but they don't have the same ID. So let's set up that situation again. We've got a list and we've got 1 extra pointer to it, B, and we've got C, which is a copy of it. And let's look at some truth conditions when we compare the 2. A is equal to B, that's true. And A is B is also true. If we look at the same conditions when applied to A and C, we can see that A is equal to C and A is C is false. And this is because the double equals operator, comparator, relies on a different truth condition than the is comparator. So the is comparator, saying A is B, it uses the ID built in that we just talked about. Saying A is B is directly equivalent to saying that their two IDs are equal. They're the same number. So that's how is works. That's what you're doing when it's essentially just shorthand for the second of those two truth conditions is to write it as the first. The double equals operator uses a double underscore equals methods. These double underscore methods are also called magic methods or Dunder methods. I'll be referring to them as Dunder methods for the rest of this talk. So what is Dunder equals? Well, it's a method on a class, and you might be familiar with some other Dunder methods, such as Dunder str, which determines what happens when the str built in is called on an object. Dunder refra, which does a similar thing but in different contexts, and of course init, which is one of the sort of Python 101 thing. So the Dunder equals method defines the behavior of that double equals comparator when that double equals comparator is used to evaluate different instances of that class. So it's a method. We can just define it on a class. So I've got a class here called my class because I'm not very imaginative. And I've defined its equals method on it, this Dunder equals, and that takes two arguments, self, of course, because it is a method on the class, and other, which is the thing that is being compared to the instance we're talking about. And I'm just going to set it to default back to that other comparator we talked about, is, which relies on the two IDs of the object being the same. So all this equals method is doing is checking whether the IDs are equal. And this is actually the default behavior of any user-defined class in Python. If you don't define a Dunder equals method, this is what's actually happening. So really, I've not done anything by defining this method other than make it extra clear that that's what it's doing. So we could also do something different. I've got a different class here that I've defined. So my named class, I'm making it so that when we instantiate it, we give it a name just so we can tell instances apart. And what I've set the equals comparator to do is to just indiscriminately return true. Every instance of this class is equal to any other instance of this class. And this can produce some really quite odd behavior. So for example, I've got two instances of this name class. I've called them A and B. And A's name is A and B's name is B. So obviously A.name is not equal to B.name, but A is equal to B, because that falls back to that Dunder equals method that I defined, and we set that to indiscriminately just return true. So even though these two things have different attributes, they compare true because that's what we told the method to do. Of course, you could go the other way. You could define a class where it indiscriminately returns false. This is great, you might think. Any instance of the class, it won't spuriously return true. It won't compare equal. Every instance of this class will be different from every other instance of this class. That's what we want, except that you end up with the behavior that A is not equal to itself, of course, because even when you're comparing an object to itself, it's calling that equals method under the hood, and that returned false. So overriding Dunder methods, it's always a risk. You should always know what you're doing. So we also, when we were talking about the ID, we mentioned that it returns, it's constant and unique for the lifetime of X. The lifetime of X refers to the span of time when X exists within the memory, that it's reachable by the interpreter knows where it is. Or the interpreter has memory that represents that object. So what happens when an object reaches the end of its lifetime? There's another Dunder method that gets called Dunder del. And this is also called a finalizer. And this is a method that is called when an object is about to be removed from memory. It does not do the actual removing from memory of the object. It is called sort of right before. If there's any last minute processing that you might need to do, let's say your object opened a file and you need to make sure that it's closed before you delete the object. That's the kind of thing that these finalizers are often used to do. And we're going to define a class that just prints out something for us when the object is about to be deleted. As before, we're going to give this object a name. So in the init, we're going to give it a name, and that's going to be stored on the object. And we're going to define a Dunder del method on this that does nothing else but print that tell us that the thing is about to be deleted, just so we've got a little bit of extra visibility into what's going on with these objects. So let's see some examples of objects getting deleted from memory. Oh, well, okay, first I should talk about how Python actually goes through the process of doing that. Python treats memory in two ways. Reference counting. Every object in memory has a number associated with it that is the number of pointers to that object that currently exist. References are pointers, pointers are references. So if you have no references left to an object, then Python knows that you don't need that object anymore because you've got nothing that can access it. You've got no pointers to it. So it's safe to delete that object from memory. That isn't always sufficient, as we're going to see. And so there is also the garbage collection, which exists in, I think, all implementations of Python, but we'll be specifically looking at CPython later on. And garbage collection is to handle the situations when reference counting is not enough to free all unused memory. So let's look at some objects being deleted from memory. We've got Dave, who is an instance of my del class. We've given him a name, and when he's about to be deleted, he will tell us. We delete Dave, and the interpreter tells us, prints out the output from calling that dunder del method. All well and good. It's worth noticing that's an instance of reference counting. There was one pointer to Dave. We deleted that pointer, and the Python interpreter knew that that object was therefore no longer needed and deleted it. So here we have a situation where we've got Alice instead. And I'm doing exactly the same thing. I'm instantiating her, but then I'm creating with also Alice a second pointer to the same object, a second reference. And that means when we del Alice, that's not the only reference to that object in memory. Also Alice is another pointer to it. So in order to get that output, that deleting Alice print out from the interpreter, we're going to need to delete the second pointer as well. Once we do that, we get the output from the del method. So now we're coming on to the situation where reference counting is not sufficient to free all the unused memory that the interpreter is using. And this occurs in a situation which are cyclic references. So before we get on to talking about what cyclic references are, I want to introduce the idea of the namespace, which we talked a little bit about earlier when we said that pointers are objects in the namespace. So you can look at it, once you've got an interpreter open, you can look at all of the names that are available to you, all of the variables that have meaning that the interpreter understands. You can inspect them by calling this globals function. And there's a ... there because it prints out a lot of stuff that we don't care about. The bit that I want to point out here is that it has, this should actually be my del class, not my class. There's an error in the slide, I apologize. It's telling us that we have this user-defined class. And that you can see that something that we have done defining this class has been reflected in this global namespace. The way that I'm going to be actually checking whether something's in the namespace is by doing this truth condition is my class in globals? It should really be my del class, but yeah, my bad. All right, so I'm going to set up a cyclic reference between two objects. You can actually have a cyclic reference with just one object, but we're going to use two for clarity here. So we've got instances of that class that I defined earlier, which has a name and tells us when it's about to be deleted. I've got Jane and I've got Bob. And these are arbitrary Python objects, these instances of this class. So we can set arbitrary attributes on them. I'm going to make Bob point at Jane by saying that Jane is Bob's friend. And I'm going to do the converse as well. I'm going to make Jane point at Bob. So by setting Jane.friend is equal to Bob. And now we know by checking that Jane is in globals and Bob is in globals, we can see that Jane and Bob, without capital letters, they exist in the namespace. If we now do del Jane and del Bob, we can see that they don't exist in the namespace anymore. The pointers that we had in the namespace now do not exist. But we didn't get the printed output from those del functions. Even though we deleted the pointers to these two objects, the reference counting didn't kick in, right? They haven't been deleted. We didn't see deleting Jane and deleting Bob. And this is because reference counting isn't always sufficient. We have set up, in this case, something called a cyclic isolate. And this is where the garbage collection comes in. We're going to be looking specifically at CPython's garbage collection. And the way that this function is, it detects these cyclic isolates. It will call the finalizers of those objects, that dunder del method. And unless, so the asterisk here is unless something in those del methods means that the garbage collection cannot proceed to the next step, the next step will be to break the cyclic references, to remove the pointers between all of these objects in your cyclic isolate. And I do actually have some diagrams coming up to explain what's going on a little bit. But before we do, the garbage collector can actually be imported in CPython. You can import GC and have a look at a bit of how it functions. So every object in Python's memory is either tracked or not tracked by the garbage collector. And if it is not tracked, that means it cannot contain pointers. If it can't contain pointers, it can't be part of a cyclic isolate. Therefore, the garbage collector doesn't have to care about it. So strings aren't tracked by the garbage collector because strings can't point to other things. So, garbage collector just doesn't care. They can never be part of a cyclic isolate, none of its business. However, lists are tracked because lists contain pointers. Arbitrary Python classes or instances of arbitrary Python classes are always tracked because they are arbitrary Python objects and you can set arbitrary pointers or attributes on them. So the garbage collector uses an object's traversal method to access all its pointers. And what that means is that every object has a list of the things that it points at. And you can actually access this list by calling the gc.getReference methods. So get reference means all the things that that object refers to. So my list containing the strings A and list points to those strings. And the way that the garbage collector uses this to detect cyclic isolates is it will essentially call that method on everything that it has in memory. And if anything eventually ends up pointing up back at itself, you know that it must be part of a cycle. So we are going to set up that cyclic isolate again. We've got Jane and Bob. We're going to set them to point to each other by making them friends, setting them as each other's friends. And then we're going to delete the pointers from the namespace that originally referred to them. So here are the diagrams, finally. I forgot where about in the presentation I put them. I apologize. This is what is happening step by step when we do that. We have Jane and we have Bob. The white boxes represent the objects in memory, and the blue names indicate the pointers in the namespace. We have Jane that points at one instance and Bob that points at another. We set them to be friends, and that indicates that, and then you can see that they now point at each other, that are forming a cycle. And then we isolate that cycle by deleting the names from the namespace. Jane with a little j and Bob with a little b, they're gone. We del Jane and del Bob. So now you can see it is a cycle and it is isolated. It is isolated from the namespace. There are no connections in. So this memory is now inaccessible from the namespace. You can't actually get at it. It should be deleted, but reference counting isn't sufficient because they still have references to each other. This one object has a reference from the other object. So their reference count hasn't gone to 0 and reference counting won't kick in, but the garbage collector can detect and deal with them. And here's how we do it. Manually, we can do this. So the way that the garbage collector normally works is periodically it will run, but you can force it to do its collection by importing GC and running the collect method. And you can see that when we do that, those two lines of output there, the first two lines of output there are from those del methods. That's the output that we originally set the del method to give us when the object was about to be removed from memory. The garbage collector's collection method also prints us out a number, or it returns a number. It returns the number of objects, unreachable objects that it removed from memory. And here it's given us 4. And you might think that it only ought to be 2 because we deleted Jane and we deleted Bob, but we also deleted their names, the attribute name that they each had. So per instance of my del class, there's 2 objects, and that's why we're getting the number 4 there. It's because we deleted 2 of those and they each also had a name. So that's how the garbage collector works. But there was that little asterisk in the slide earlier. What happens if something in the del method, the dunder del method, means that the garbage collector can't proceed to breaking the cyclic references? Oh, and I should say, it breaks all the cyclic references, and at that point, the reference counting kicks in. So actually, the garbage collector, all it does is reduce things down to a state where reference counting becomes sufficient again. Anyway, what happens if the garbage collector cannot proceed to that final stage? So fun with finalizers. So the entire thing about a cyclic isolate, the problem with it, the reason that memory needs to be got rid of is because it's isolated. There are no pointers from the external namespace to within the isolate. But you can create pointers outside the isolate in the finalizer, in the dunder del method, by creating a new global variable. And that's exactly what we're seeing here. So this is a modified version of the class we've just been using, still has a name, all of that's the same. But when it's about to be deleted, it creates a new global variable within the global namespace, and it sets itself to be equal to that variable. It assigns itself to that variable. So what will happen when we actually try and run this? We're going to do the exact same thing that we did before, setting up the cyclic isolate. This is setting Jane and Bob, making them be friends, deleting them from the namespace. But we're doing it with this new bad class with with a modified Dunder-Del method. Now, if we hit garbage collect, if we try and trigger the garbage collection, it will print things out. It will print out the output from those finalizers. But the number that it's given us is 0. It hasn't deleted any unreachable objects. And if you'll remember, go back to that slide, the point at which it sort of aborts the process is after having called the finalizers. So it's called the finalizers of these objects. And it's worth noting here that it called Bob second. Bob is the second of the 2 objects who had his finalizer called. But it didn't actually break the cyclic references and allow these objects to be deleted by the reference counting. And if we look in our global namespace again, we can see why that is. It's because that global person variable that was created by the del method, by Bob's finalizer, exists in the namespace. It created a new global pointer that points to within the cyclic isolate. That cycle is no longer isolated. So the garbage collector can no longer, in good conscience, break all the cyclic references and allow it to be collected by the allow it to be deleted because of reference counting. So what happens if we look at this person pointer that we've now created in the namespace? We can inspect it. We can say its name is Bob. And the reason that it's Bob and not Jane is because Bob is the one whose finalizer was called second. He was the last one to say, oh, global person is me, I'm person. But you can see that it still has a reference to the other object, Jane, through person friend. So both these 2 objects have been kept alive in memory by this global pointer that we created in their finalizer. And here's an example, here's a diagram to kind of explain a little bit what happened. That Dunder-Del method created a new reference from outside the cyclic isolate in the wider namespace, meaning that the cyclic isolate was no longer isolated. And therefore the garbage collector, what it does at this point is it just like throws up its hands and goes, I'm not touching that. So we've now created this really bad situation where these objects are not referred to by their original pointers, but what can we do to resolve this situation? Well, if we're looking, you can see that the original pointers don't exist. Jane, the object, the white box still exists, but Jane, the name, doesn't. What we can do, of course, is we can say del person, we get rid of that pointer from the namespace, and we call the garbage collection method again. And what happens when we call the garbage collection method again is that it just deletes the object. It does not call their finalizers again. The finalizer of a Python object can only ever be called once, and that is specifically to avoid the situation where we just end up in this endless loop of it creating a global variable and keeping itself alive. So you can see here, it did not call the finalizers. We did not get that text printed out, but we did get the number. It did detect that there were 4 unreachable objects, Jane and Bob and their names, and removed them from memory. And with that, that is the end of pointers in my Python. I hope you all enjoyed it, and it's been a delight to present to you. So thank you very much.
Thanks a lot for the talk, Ila. Now we can take some questions. So if you have any questions, type it in the chat or in the Twitch chat. Oh, we have a question. Is it possible to disable garbage collection?
It is.
And manage all the memories manually?
It is. So I forget exactly how it is. The documentation is really good for CPython's garbage collection. There is, you can set the level at which it collects. You can set how often that collect method will be triggered in the background. You can set it to be never, essentially. You can also alter various things, like, so when there's, I'm trying to remember exactly how it functions. There are certain pools of objects. So there are objects that haven't been referenced in a while, and then there's objects that certainly, there's objects, the way that it functions is it will only check some of the objects that are in memory. Ones that have been accessed recently don't get checked. they're assumed to still be live. If they haven't been checked for a while, they go into one pool. And if they haven't been checked even longer, they go into another. And those are the ones that get prioritized by garbage checking. You can alter how many pools there are as well. I think it's called generations is the terminology for it. But you can also set it to just never run the garbage collection at all. I think the method you can call gc.disable. There's actually a method for it. And if I was doing like a live demo and I wanted to make sure that the garbage collector didn't go off accidentally while I was coding, I would do that first. Yeah.
Yeah, there is a follow-up question. So about disabling to get a bit more performance, or it doesn't affect the performance?
Oh, I mean, so if you're thinking about getting really good performance, you're going to want to care about what implementation of Python you're using. Probably most people use CPython just generically, unless you're working on really constrained memory, in which you're using MicroPython. It really depends what you're doing for how you're going to want to optimize for performance, and memory management might be part of it. Yeah, I mean, finer control over what the memory management, what's happening with regards to memory, probably wouldn't hurt for optimizing performance. I'm not going to say that it's necessary, but if you are going to want to improve your performance, you're going to want to have some understanding of what's going on under the hood, and maybe to directly manage it, or indirectly manage it by coding in ways that encourage the garbage collector to do what you want. So being very careful to not set up cyclic isolates or some such, or to call garbage collection yourself explicitly once in a while, or to disable it and do it all manually. There are a bunch of approaches, and what you're doing is going to dictate which one is going to be best.
I have a question actually. So these cyclic isolates that you mentioned, how actually the garbage collector finds them? So when does it kick in to delete them? Do you know something about that, or?
So by default it'll happen every once in a while, and how long that is configurable. It's related to the generations thing that I mentioned earlier. Again, I would need to go and look at the documentation again to give you a precise answer, and at which point I might as well just say go and look at the documentation because it's really good. Yeah, and the way that it detects these cyclic isolates is by looking at what everything, it basically can sort of draw the graph of what everything points at, and then detect cycles within that graph. And once it has detected a cycle, it's fairly trivial to determine whether or not that cycle is isolated.
Mm-hmm. Thanks. We have another question. Could you also explain the swap method in Python? Well, is this, I think, too specific probably?
I have a feeling this is one of those things that gets asked in interviews, or sort of a basic Python thing that I just don't know. I've not heard of this before. I bet it's doing something really clever in order to manage, like, to swap the pointers, but
yeah, it's probably very specific.
I imagine it's just swapping pointers, so making B point at the object that A pointed at and vice versa, but I don't actually know that, so sorry. I'll put it on my list to learn about and explain.
All right, so there are any more questions? Please write in the chat, but I think we don't have more questions for now. So yeah, thanks again for the very interesting talk.
Well, thank you very much for having me.
Yeah, pleasure. And I think we are at the end of the meetup for today. Yeah, I don't know if we will have a closing session, closing few slides, or we're just going to.
Yeah, I think they should be visible already.
Yeah.
Okay, so thanks so much to all of you for attending today's PyBerlin, and thanks especially to today's speakers for sharing their knowledge with us, and of course to our sponsor Scalpy for providing us with a premium Zoom account. Our next meetup is scheduled to take place on October 18th. And a quick reminder that everyone is very welcome to contribute to PyBerlin, and we can always use some extra help. So please reach out to us if you're interested in helping out. We are also looking for people willing to speak at PyBerlin. So if you have an idea, you can submit it using the form linked on the slide. And please don't forget to spread the word about PyBerlin. Enjoy the rest of your week. Take care and see you next time.